After this incredibly simple example of it not mattering whether you take the point of view of the coil or take the point of view of the magnet, Einstein says, let's raise this idea that physics should be the same in all constantly moving frames to a principle, to a starting point of his physics. We'll call it the relativity principle. But we need another. Einstein had noticed that Maxwell's equations never predict a wave traveling at any other speed than 186,000 miles a second. You simply never can catch up to a light wave. This is an idea that Einstein had been tortured by ever since he was a boy of 16. That if you could catch up to a light wave, you would see it like a simple set of hills that were static in front of you. You would never see any motion. There would be this just changing electric field as you went farther away from you. But no one ever sees that. So neither experimentally nor theoretically did there seem to be any reason to think that light could travel other than 186,000 miles per second. So Einstein says, let's make this our second principle. Light always travels at 186,000 miles per second, no matter how I'm moving. Well, there seems to be a contradiction here. The laws of physics are the same in every frame of reference, and no matter how a source is moving around and sending out its light signal, it always seems to be traveling at 186,000 miles per second as soon as the light's been sent from it. What if I'm racing towards it? Aren't I forced to say that I'd see light traveling faster than 186,000 miles a second? Or if the firefly was flying away from me, wouldn't the light look slower to me? So he says the problem is that we need to analyze what we mean by time. This quantity that ever since Newton had seemed to be obviously perfect, absolute, mathematical, beyond any experience. There seemed to be an absolute time in the world. Well, Einstein said, no, we need to look at it more carefully. That's the surprising part. Einstein's saying we need to reanalyze the concept of time. It is this questioning of time itself, up front, at the start of his theoretical reasoning, that contemporaries like Hermann Minkowski saw as the crux of Einstein's argument. As Einstein put it, we have to take into account that all our judgments in which time plays a role are always judgments of simultaneous events. If, for instance, I say, the train arrives here at 7 o'clock, I mean something like this. The pointing of the small hand of my watch to 7 and the arrival of the front of the train are simultaneous events. For simultaneity at a point, like right in front of my nose, there's no problem. If an event located immediately next to my watch, say the train engine arriving right there, happens just when the small hand of my watch hits the 7, then those two events are said to be simultaneous. The difficulty, Einstein insists, comes when we have to link events at a distance. What would it mean to say two distant events are simultaneous? We can't use a central clock naively. It leads to inconsistency. If I set all my clocks when they get a signal from my master clock striking 12, then I have a problem because it gets to the near clocks sooner than the far clocks. So if I moved my central clock, I get a different result of what's simultaneous. A better account would be this, Einstein says. Figure out the time of travel by a round-trip exchange. Say it's a 2-second round trip, then I say it must be a 1-second one-way trip, and so I can set my clocks. If my master clock strikes 12, the clock that's 1 second away by light signal sets its clock to 12 plus 1 second. Let's go back to Einstein's train. You will recall that he wants to know what we mean by the arrival of a train in a station at 7 o'clock. I've long read this as an instance of Einstein asking a kind of imaginary thought experiment question that only a child would ask, as he liked to put it. A question so elementary, so basic, that it lay below the conscious awareness of the physics community. But was it in fact below the threshold of thought? Was no one else in 1904, 1905, in fact, asking what it meant for a distant observer to know that a train was pulling into a station here at 7 o'clock? Was the idea of defining distant simultaneity such a philosophical reach? One summer I was standing in a northern European train station, absent-mindedly staring at the turn-of-the-century clocks that lined the platform. They all read the same to the minute. Curious, I thought, good clocks. But then I noticed that as far as I could see, even the staccato motion of their second hands was in synchrony. These clocks were not running well, I thought. These clocks are coordinated. Einstein must have seen such coordinated clocks in train stations while he was grappling with his 1905 paper, trying to understand the meaning of distant simultaneity. Now, this problem of coordinating clocks in train stations and among different train stations scattered far and wide over continents and countries was a problem of great concern. Let's go down to the collection of historical scientific instruments where we can see some of the Harvard clocks that were based at the observatory here and used, in fact, to set clocks all over New England. Today, Richard Ketchen's here. Richard's an expert clockmaker and somebody who's been involved with this collection of timekeeping devices for decades. And I'm hoping that you can tell us a little bit about the clocks that were used to distribute time in New England and keep time for astronomical observations.
I'd be glad to. Let's take a look at them. This was made by William Bond and Sons here in Boston, and it's a very accurate, what we call astronomical regulator, or jeweler's regulator. It's laid out with a typical regulator dial where we have the hours at the bottom, the minutes around the outside, and the seconds at the top.
This clock was in the observatory?
Yes, it was. This is really the heart of the accuracy of the clock. This is what's called a temperature compensating pendulum, and it has a jar full of mercury down here at the bottom. When the temperature rises, the steel rod will expand and the pendulum will get longer, but at the same time the mercury expands and it gets higher, and the height of the column of mercury has been accurately determined so that they will cancel each other out and the timekeeping will remain the same.
So you want this temperature compensation because from a New England winter to a New England summer, you're looking in Boston at a spread of what can be over 100 degrees.
Yes, indeed, and that would represent a couple of minutes a week.
So could you take off the bonnet?
Yes, we can do that. This one is jeweled, probably in sapphire, and you can see the escape wheel going around and you can see the pallets oscillating back and forth.
So this clock was used to distribute time.
It was used in, I think, 1853 with the Boston and Providence Railroad, and it was used as their standard timekeeper.
And how did they send the time?
They would send the time through some electrical contacts that were automatically made at the 60-second mark. And they would use this to not only check the accuracy of this clock, but to send a time signal out to other clocks so that whoever was watching the clocks could make sure that that second hand was right up there at the 60-second mark when the electrical contact made a tick on the chronograph.